Hello everybody. Today we're going to talk about transformations and how that relates to similar figures. Okay, what are similar figures? We have talked about the symbol of that before. The little squiggle means similar. But these are figures that have the same shape, but not necessarily the same size. Okay, so I always like to compare it to, for example, maybe like a piece of paper, an 8 by 11, 8.5 by 11 piece of paper, and then either like a TV screen or a whiteboard in the classroom. So again, they're the same size. They're both rectangular, but they're not both the same shapes. I apologize. Both the same shape, not the same size. Not the same size. Okay? So here's an example of one right here. So we've got a quadrilateral. Looks like a trapezoid. Again, can't necessarily confirm that. But those would be similar. So again, same shape, not the same size. Okay? Congruency, on the other hand, preserves length and angle measures. So they are not only the same shape, but they are the same size. Similarity preserves angle measures. Okay? So angles are congruent. So angles are congruent if it's similar. So if I know that these are similar, here's my little similar sign. I know that angle J and angle Q, right? Angle J and angle Q would have to be the same angle measure. Okay. Similar figures are also proportional. So again, the ratios of their corresponding sides are equal. Corresponding sides are equal. So it's not necessarily the same measures. So let me give you an example of that. I'll just draw something down below here. So if I'm looking at, again, let's just call these two rectangles here. Sides are, and they're similar. Okay, gotta know that. So I could set up the ratio of 2:4 as 3:x. And then we can easily just cross multiply and figure out that this side x would be 6. Okay, so it'd be what we would call, depends on which direction you would go with that. You would say it's in a 1:2 ratio. So in other words, it's a dilation. Oops, 1:2 ratio. I forgot the 2. Okay, and that's where our transformations come into play, because we're talking about a dilation. A dilation will change the size of the original figure. So let's try an example here. We're going to graph a segment in points 12, -6, and 0, -3. So let's go ahead and just do that real quick here. So there's my B of 0, -3, and then 12, 11, and that's going to extend off just a little bit, all the way down to -6. And that's going to be A. So there's my segment. That's my original segment. Okay. We also want to graph its image after we do this transformation. Okay, so we have two of them going on here. We have a reflection over the y-axis. So it's going to flip over the y-axis, and then we're going to dilate it. So if you remember, a reflection over that y-axis negates the x, leaves the y the same. So kind of what we've talked about before, you can do this in 2 steps. You can do the reflection first, so you can take your endpoints here of 12, -6, do a prime with your reflection, then go over to a double prime. Or you could just go combine these two together. So combine the dilation of a third. Okay, and I'm going to go ahead and just simply do that. Let me move this down just a little bit here so I have a little more room. And I'm going to write my other ordered pair, my original ordered pair. And again, I'm going to go right to combining this. So the only thing that would change is I now would make my x -1/3 and y would be a third. So I'm combining the reflection and the dilation there. So in this case here, so negative a third times 12, so a double prime, again, because there's two of these happening here, would be negative 4, and then take my y and multiply by a third. So I'd get negative 2. Same idea here, so that would simply just be 0. 0 times anything is itself. Negative a third times a third, that would give us negative 1. So again, we're always able to identify the order pairs. Now we can graph it. Zero, negative 1. Label your points. You must label it on the graph. So not only graph the points, but label with A double prime, B double prime. Okay, so you can see that this was a dilation. It's still a line segment. However, it is similar because size is not preserved. So here we have a transformation that maps trapezoid WXYZ to trapezoid PQRS. Okay, we want to describe it. All right, so the original one is the blue one, WXYZ, and it maps that trapezoid to the larger one, green one, PQRS. Okay, so what is it actually doing first? So hopefully you can see here, I'm going to compare a couple different things. I'm actually going to take a look at Y, which then maps onto R. So it does a few things. Hopefully you see that, yes, it's going to actually flip it. It's going to reflect it over that x-axis. Because the general shape, the slant, this slant, it's again flipping over this x-axis here. But we clearly have a dilation. Well, let's think about this. This would be negative 1. That maps to positive 2. Right? Okay, so we can take a look at another one, Z to S. So Z, this goes from negative 1. Now that also goes to positive 2. Okay? But it also moved my x's. So my x here was 2, then it went over to 4. So hopefully you're realizing, yeah, I'm doubling my y's, but I'm also doubling my x's. So I'm dilating by 2. So in other words, if you think about your order pairs, this is what you would be doing. 2x, 2y. Reflects over the x-axis, that would make your y's negative. So this portion here would be doing x and making them the y's negative. Again, you can combine those. But it simply just said describe, so this is what we're looking for when it said describe. Okay, what I did there in terms of the order pairs is the process we would actually go to come up with that transformation. And again, you're going to need to be able to do that as well, but just make sure you're answering what they're asking for here. Okay, and we just simply did that by looking at our diagram and breaking that down. All right. Last one, determine whether the polygons with the given vertices are similar. Use transformations to explain your reasoning. So what they're saying here is ABC compared to DEF. Okay, so ABC compared to DEF. Are they similar? Yes, no. Yes, no. Why? Okay, let's first graph them. So I'm going to graph ABC. First, I'm going to graph that in red, so we'll go 6, 0. Actually, go ahead and pause this video, graph these, draw them out. So obviously you have two triangles, the green one and the red one, and then push play when you're ready to resume. Okay, so there are our two triangles. We're taking A and the red one, ABC, and mapping it onto the green one, DEF. Are they similar? Okay, so hopefully you see that they are. It's obviously a dilation, and then it's shifted. Looks like down and left. We can double check that. It might actually be up. So we can go through that and take a look here. But it is a dilation. And then again, we're going to have a translation. We got to figure out what that is. And it looks like it is left something. And actually, I originally said down, but I actually think it's up something. And we can verify that. We can verify it algebraically. We can kind of think through this process. The reason I think up is because I got to move A up, right, to get to this D part, because those map onto each other. B, again, so we got a few other things going on here. We got to move it, right? So let's take a look. Let's see what's going on with this one. Okay. One way of actually doing this is you can set up a systems of equations. You can do this by looking at your x values and then your y values. Okay. So I first take a look here at my x values. Okay. So I'm going to look at 6 compared to 0. Right? So we are thinking that we have a dilation going on here. So I have to take 6 times some value if I'm dilating it. I've got to add something to it to translate it to move it left or right. We'll figure out again if these are correct. And then it's going to end up being 0. Because I'm taking this 6 value and doing a transformation to get 0. Well, now I got to do it again with another x value. So 9 times some dilation of A plus something to get me over to 1. Okay? So now I have a nice system of equations where I can actually solve this. So if I multiply this all by a -1 here, and then I add those, I get 3a, b's cancel, and then I get 1. A is a third. That's what I'm dilating by. Okay. Then I can plug it back in. 6 times a third plus b equals 0. So this is going to give me 2. Subtract that over. So it looks like I'm going -2. So that's going to be left 2. So my mouse stopped working there. Okay. Well, let's check this out with our x values. I'm sorry, our y values. Okay. So same idea, but now this y value here has to map onto that y value. So let me extend this page just a little bit. Let's check this out with our y's. So again, our y's. So I started out with a y value of 0, had to multiply it by some dilation, and then I had to add something to it, so we'll call that b, to get over to 3. This one's very nice, because right away it gives us a value of b equals 3. Okay, but let's talk about this just a little bit. Let's keep going. We need another y value. 6 times some dilation of a plus b is going to equal 5. So 6a plus b equals 5. Well, since we know b already equals 3, plug it in and solve. And it hopefully should be a third. And guess what? It is. So my dilation is definitely a third. This means I'm moving b. I'm moving my y values up 3. So again, my dilation would be a third x, a third y. After that, I would take my x and subtract 2 and add 3. Again, step 1, step 2. So you're dilating by a third, then you're moving it left 2, up 3. Okay? So the answer to this is yes. They are similar. And here's your reasoning, your rationale. Dilation of a third, left 2, up 3. Okay? All right. So this concludes chapter on transformations and similarity regarding transformations.